Yesterday, we were talking about the multiplication rule for and things. And we said the probability of A and B, what did we do? We multiplied their individual probabilities as long as what? Good, they were independent. Section 5.4 says, well, what about the and kind of probabilities when they're not necessarily independent? And that's called conditional probability, and that's what we're talking about today. So, I've got this hand of cards right here, and I'm going to draw two out. What's the probability of both of them being black if I replace the first card after I draw it? Well, that's going to be the probability of getting a black card first times the probability of getting black card second time, right? Are those independent? Based on what we said yesterday? Does the fact that I drew a black card or didn't the first time affect the probability of a black card the second time if I'm replacing the card? No. So I can do that. I can do yesterday's rule. That's what I'm doing right there. So what's that going to be? Well, the probability of a black card on the first one, there's 3 out of 6. And then since they're independent, it's going to stay that for the second. So a fourth of the time, if I repeated this little experiment thousands and thousands of times, I would expect about a fourth of the time I'd get 2 black cards. Now, let's change it up. I'm not going to replace the card. So I want the probability of getting 2 black cards without replacement. So the probability of black on the first one times probability of black on the second. This looks the same. Let's figure out what they are. Probability of black on the first one. 1/2. That didn't change. But now I take that black card. Let's say I got the queen. And I'll lay that card on the table. And now then, whoever I'm drawing the cards from have 5 cards in their hand. And I'm going to draw another card. What's the probability of that one being black? Hmm? 2 out of 5. Good. Because there's 2 black ones left. There's 5 cards left. So I'm getting 2 out of 10. So a fifth of the time now. Look what changed. The probability went from happening a fourth of the time to a fifth of the time. Why? Because I put a condition on things. I said I'm not going to replace the card. That condition changes everything. Yes, ma'am.
Are we using that as like the example, like for this? Is that picture what we're using?
Yeah.
Okay.
I probably should have made it more plain what I was doing. I changed the conditions. So the reason I call this conditional probability is you're saying, what's the probability but under these conditions? Get this notation down, please. Okay, this notation means the probability of F happening given that E happens. So I'm basing the probability on one thing based on whether another thing's happening or not. See, those are not independent. In other words, here, the fact that E happens is changing F's probability. Just like in our card drawing thing. Now, that bar is not division. It means given that or knowing that. I think knowing that might make more sense. So knowing that E happens, now what's F's probability? Okay, we got 6 people in here right now. 3 guys, 3 girls. If I said, I'm going to give a donut to one person in this room, the probability of any one of you getting the donut is what, 1/6? What if I say, I'm going to give somebody in this room a donut, but it's going to be one of the girls? Now then, each of them has a 1/3 probability of getting the donut. The guys are shut out. Their probability is 0 of getting a donut. I changed one condition. I restricted my sample space. Okay. So in our first experiment with the cards, the probability of getting a second card that was black also was 2/5 once I knew the first card was black. This is the conditional probability rule. It's saying the probability of B knowing that A happens is a fraction. It's a fraction with the probability of both A and B happening on top and the probability of A on the bottom. So it's a probability, and it's a fraction. That's what most probabilities are, right? So we've got the probability of the second thing happening, knowing the first thing happened, is just this fraction. And if you look at the top, isn't that the overlap of A and B? Yeah. So we got 2 sets of values here. Set A has 1, 2, 3, 4, 5, 6, 7, 8 in it. And set B has 4, 5, 6, 20, 30 in it. So I made a Venn diagram. Just got the numbers in those 2 sets. Notice I colored the overlap yellow because they share 4, 5, and 6. Are A and B disjoint? No, there's an overlap. So these are not mutually independent or mutually exclusive. So, something else to notice is that fraction up there is just a proportion. Before you write anything, just take a look with me. That fraction, the probability of A and B divided by the probability of A, is just a proportion. It's really saying in English what I wrote down there at the bottom. What's in the overlap divided by what's in A. Well, when you put it like that, how many things are in the overlap? 3. How many things are in A? Be careful.
8.
Thank you, 8. In other words, we don't really care about this out here. What are we doing, y'all? We're restricting our sample space for this to just A. I know that formula is there and everything for the rule, but realize what's really happening. We're just saying, if I just look at A, what's the probability of getting B? And that's going to be the overlap divided by all of A. It's just a proportion. In the donut deal, What was it? If I restrict this to just girls, what's the probability of one of them getting a donut? 1/3. I look at it as a restriction of the sample space. I hope that helps you. People get confused on this every year. They say, I don't understand that conditional probability stuff. It's just a proportion. What proportion of A is in the overlap? Yes, sir.
What if you like see, instead of saying what is in A,
Uh-huh.
like, can it be what is in B?
Yeah, it would then, this part up here would be changing the probability of A given B. See, if we're looking at B, then it would be that overlap divided by what's in B. And if you looked at it like that, now then what would it be? What's the probability of A given B? See, now I've restricted the sample space to just B. And so then that'd be what? 3 out of 5. Yeah. But it would change this back over here to A given B happens. And down here, this should be B knowing that A happens down there. Okay, not hard. It's just a fraction. So let's look at a couple of these. This is the kind you want to see on a test where they've got a table and everything's laid out for you and they've got the totals. If they don't put the totals, that means you've got to figure them out. So look at our first one. I'm going to reach, this is all this data. I'm going to reach in a hat and I'm going to pull out one name. And my first thing here says, okay, what's the probability you got a male's name knowing that you drew a married person? What's this doing? It's restricting who we're looking at to just married people. Y'all with me? This part out here is our restriction, our condition, if you will. So I'm just going to look at married people. Now, y'all, this comes down to either a row or a column. So if I'm looking at just married people, I'm looking at these folks. Yeah? So, given that I'm just looking at them, now what's the probability there's a male? Well, 63.3 divided by the total out here, 125.3. And to 3 decimal places, what is that? Please. Thank you. Okay, so a little over 50% of the time, if I draw a married person, I've got a male. Okay, let's change it up a little bit. The second one says, I just drew out a name. I'm telling you it's a male. There's my condition. It's a male. Now what's the probability I drew a married person? So I'm doing what you said. I'm restricting this to males. And so I'm getting what now? 63.3. But my new sample space is just males. Over 126.9. Which equals about what? Thank you. Okay. I reach in there and I get a widowed person. That's my condition. What's the probability that I drew a male's name? So here's widowed. So 3.3. This is not hard once you realize what they're really asking you. Oh, it's 15.2, isn't it? Oh. 0.217?
Yeah.
Thank you. And so now then, let's do the same kind of thing. I drew a person's name out that's widowed. What's the probability of female? I'll leave my highlight where it is there. Thank you both. Now look at that, y'all. Are men and women widowed at the same proportions? No way. If I'm telling you I just got a widowed person, the probability that I drew a female's name is almost 80%. So there's a lot more widowed females than there are males, right? Okay, let's keep going. This is conditional probability. Let's try a word problem. No table. Okay, 12.7. I'll let you read it. I won't read it to you. I think that Venn diagram will help you. So I've got two intersecting circles. So let's call the first one here a Venn diagram will help. Let's call this first one preterm. So I'll put P out there. So that first circle is all preterm babies. I could have made the other one preterm, and there's nothing magic in that. I'm just going by the order that the problem has. And there's 12.7% in here. Let's keep everything percents. So in that first circle, 12.7. Let's call this one over here B for big kid. Okay, it doesn't tell us much about them, but it does tell us that 20.22% of all births resulted in a preterm baby who was a big kid. So that's my overlap, isn't it? They don't specifically say there's your overlap, but you got to kind of infer it. So I'm going to put 0.22 here. Now, I just threw off the number I put in P because that should include that 0.22. Y'all see what I'm saying? So over here, the point that's not in the overlap should be that. If I add 12.48 and 0.22, I get 12.7. So I'm keeping everything percents. So they want to know, what's the probability if I just pick a random baby and know that it's preterm, what's the probability that kid's going to be a big kid? So I'm really using that conditional probability. So the probability of getting a big kid, knowing that he or she was preterm, is what? Well, what's the probability of preterm? It's just a, think of it like this. Where's the overlap? 0.22. That's in the overlap. What's in P? 12.7. I'm keeping everything a percent. What do you get?
0.0173.
That? Okay, thank y'all. All right, so now then, that says what? If I draw a baby's name out and I go, oh, this is a preterm kid, what's the probability it's going to be 8 pounds, 13 ounces or more? 0.0173, so less than 2% of the time. Now, I think normal term is somewhere around 39 weeks, so the last few weeks make a huge difference in the weight of the baby. They're growing really fast right there at the end. Make sense? Let's do another one. Let you read it. Okay, so we got two things going on here. Women with bachelor's degrees and marriages lasting 20 years or more. So let's make one of these circles women with bachelor's degrees. So here's B for bachelor's degree. We'll let this one be L for lasting longer than 20 years, or at least 20 years. Now, what are they asking us for? The probability of randomly selected marriage. So I'm just going to pick a marriage at random. What's the probability that it will last 20 years? They don't put the words given that, but look right here, if. You got to translate sometimes. So at least 20 years given that the woman has a bachelor's degree. Well, how many women have bachelor's degrees? What's B, in other words? 35? Where's the overlap?
47.
Good. That means I got to change this to 8, right? So now then B has 35 in there. We don't care about this out here. It's not part of the question. So it's asking for the probability of a long-lasting marriage given that the wife has a bachelor's degree. Okay, so probability of L and B. If you want to write the fraction out, but we know it's just going to be a proportion. So I'm going to skip that formula part. Once I've got it to where I know what's going on, what am I going to do? Where's the overlap? 27. Divide by 35.
0.771.
0.7 what?
771. 0.771.
771. Okay, I wasn't picking up that middle number. All right, 0.771. So if I reach in a hat and I draw a marriage out and I go, oh, the woman has a bachelor's degree, the probability that that marriage will last 20 years or more is over 75%. Okay, that's a good sign. Questions, y'all? I know I'm going through this fast, but there's a lot to cover in our one little class time here.
I think he's a question.
Wait, sorry.
He's not understanding it.
No, I understand. I'm just like, building it out.
Okay, that's
So-
good.
That 52% of all marriages last at least 20 years, can you put that in L too? Like that.
You could. Okay, that's a good question. What would go out here? If I know 52% of all marriages last at least 20 years, what has to be the rest of L if it totals 52? $25? If I add 27 that's in L, the overlap, to 25, don't I get 52? So there would be a picture of the whole thing. Now let me ask y'all something. Since you brought this up, that's a good question. What if I turned it around and said, what's the probability of a woman having a bachelor's degree? I'm choosing a marriage at random. What's the probability of getting a woman with a bachelor's degree given that it's a long-lasting marriage? It would turn it around, and then the fraction would be what? 27 out of 52. Whatever that figures out to be.
25.
Okay. So you could ask it either way. This particular question asks one way. Good question.
Thank you.
Let's see. Let's maybe skip that one. I don't know. I want you to have that clock's not right anyway. Okay, let's try this one. The probability that a randomly selected adult, all of these people are adults. I'm going to randomly choose one. What's the probability that he or she uses social media given that they're in the 18 to 34-year-old range? Look what I'm doing. The given that restricts my sample space to that. So what's that going to be? Probability social media given that they're in the 18 to 34. 117 over 150. Let's just leave it like that and not worry about the decimal places. Y'all with me? Okay, let's change it. B says, what's the probability that a randomly selected adult is in that age range, knowing that they use social media? So that means I got to take this one out and restrict the sample space to social media users. These are easy if you know what's really going on. So once I do that, now then what proportion of those folks are in the 18 to 34? Right. Um, and then the question says, how would you show that 18 to 34-year-olds are more likely to use social media? What would your argument be? Okay, if you just put the percentages on it, that'd be wrong. You got to be a little more detailed. You can't say it's Wednesday. Yeah, it is true. It is Wednesday, but that's not a good enough reason.
Yes, because out of 338 people, 6% once I mean, is 234 years.
Look at A. What's A telling you? That if I draw a name out and I know, I'm sorry, it would be, let's see. It'd probably be B, wouldn't it? If I know somebody uses social media, the 18 to 34-year-olds would have a huge proportion of that. Much more so than any other group. So, that's how you'd make your argument. Take this. That's the conditional probability rule we were just working with. And then I'm going to multiply both sides. I'm going to get rid of the fraction there. Multiply both sides by the probability of A. That's all I've done. Multiply both sides by the probability of A. And then I'm just going to change sides with the result and get this. Now, yesterday, we talked about a rule for and kind of things. And it was a multiply rule, right? It was version 1. And to use it, the two events had to be independent. Well, here's a rule, talk about the probability of A and B. And it doesn't look quite the same as yesterday's. So what we've got right there changes into this. This is version 2 of the multiply rule. It's what was at the bottom of the... I'll go back if you need me to. So the multiply rule has 2 versions, like the addition rule did. And this one says, it's not enough just to multiply the 2 probabilities. That second one has to be knowing that the first one happened. It's got to be conditional. It's got to be conditional. Think about our first example with the cards. That really was using this rule. Right? The probability of A was 1/2 of getting 1 black card. And then I don't replace that card, and the probability of the second one being black had to do with whether the first one was or not. And it became 2/5. Okay. Notice something. Just look at this. Don't write yet. Look at this. If A and B are independent, doesn't that part right there just become the probability of B? In other words, think about it. If A doesn't affect B's probability, isn't where the arrow's pointing just the probability of B, if they are independent? So this is called the general multiply rule. which means it works under any condition, whether they're independent or not. If they are, that just becomes a probability of A times a probability of B. If they are not independent, then it becomes conditional, like we've been talking about. Flying in a helicopter up over the interstate. I'm going to pick a driver who is speeding. Should be pretty easy. So I just randomly choose a speeding driver. Then I'm going to say, okay, what's the probability that that driver gets pulled over? Well, it's 80%, 0.8. Now then, I watch to see if that driver gets a ticket. And if he or she gets a ticket, the probability is 0.9 if they've been pulled over in the first place. And I repeat that over and over and over again. I want to know in general, what's the probability that a selected driver who is speeding gets pulled over and gets a ticket? Okay, so we got a couple of things going on here. Let's let P be pulled over. And T gets a ticket. Okay? So I want the probability that a driver gets a ticket knowing that they got pulled over. Part of this is reading the question and translating it into something you can use. So I'm looking back at the question. What's the probability that a randomly selected driver who is speeding, there's your given that, gets pulled over and gets a ticket? Okay. So the probability of being pulled over times the probability of getting a ticket. I just did that completely wrong. Hold on. This is an and thing. I'm still thinking the conditional probability stuff. All right, so the probability of getting pulled over and getting a ticket is the probability of getting pulled over times the probability of getting a ticket knowing that they were pulled over. That's what it should be. What's the probability of getting pulled over? Knowing that somebody was pulled over, now what's their probability of getting a ticket? It is. So the probability that a random speeding driver gets a ticket is that. Conditional probability. Okay, so we got a manufacturing error. They accidentally filled regular soda cans with diet soda and put them in a 12-pack. Now I'm going to choose 2 cans out of there, and we got some questions about it. So on this kind of thing, I think it would help you to make a drawing. There it is. So I've got diet, diet, diet. I've got, here's regular. So what is that? 8, 9, 10, 11. So there's my pack. Going to draw 2 cans out, the probability that both are diet. So I'm going to say probability of diet on the first one and diet on the second one. It's an and thing. Equals probability of diet on the first one times the probability of diet on the second one, knowing that we already got one diet out of there. What do you think? This is like the card thing. Just different numbers. What's the probability of getting a diet on the first one? I draw a random can out. 3 out of 12, thank you. Now, so that one's gone. What's the probability of getting a diet on the second one, knowing that I got a diet on the first one? So 6 out of 132. Let's just leave it a fraction. I could reduce it, I could change it to a decimal, but let's just leave it like that. Okay, so there's A. B is saying, what's the probability that both contain regular? So regular on 1 and regular on 2. Well, the probability of regular on 1 times the probability of regular on 2, given that we already got one regular. So I get regular on the first one. Its probability is what? 9 over 12? Okay. And then the probability of getting a second regular.
8 over 11.
So I'm getting 72 over 132. We good? Now, the last part says, what's the probability exactly one is diet and one is regular? Well, diet and regular. Watch out on this one. That's how I'd notate it. But let's see what that's going to turn out to be. So diet on the first one, 3 out of 12. So one of those is gone, and then regular on the second, 9 out of 11. So 27 out of 132. And if you stop there, you'd be half right. Because all we did was figure diet first, then regular. What if I got regular first, then diet? Isn't that another way to do it? So I'd have to multiply that answer by 2. So I'm getting 54 out of 132. 2 ways to get into the same answer. Are those disjoint ways? Yeah. Diet then regular is different from regular than diet. Interesting. Watch out for stuff like that. Okay, I'm going to skip that one. How would you show 2 events are independent? I could really easily ask you, here's a setup. Are these 2 events independent? And here's how you show it. We've alluded to this before. If the probability of A, just by itself, is the same as the probability of A knowing that B happened, if those 2 things are equal, did B influence A at all? If the probability of A is the same as the probability of A knowing B happened, did B influence A's probability? No. So they're independent. That's the definition of independent, right? Or is the probability, you don't have to do both. If the probability of B equals the probability of B given A, that means A didn't influence B at all. They're independent. Well, when would that ever come up? I don't know, maybe some question like this one. Okay, we've got that same table we've been working with. It's wanting to know, are widowed and female, those are two events. Widowed is one event, female is the second event. Are they independent? Now, from what we did before, we wouldn't think so because there's a lot more widowed females. We think gender has something to do with this. So what am I going to do? What's the pick one. You want to go with widowed or do you want to go with female? It does not matter. Okay, I heard female first. What's the probability of female? Just female is 133.2 out of 260.1. Yeah? Okay, what is that decimal? Let's go ahead and do a decimal on this one, please.
0.512.
Thank you. Okay, so that's just, if I drew a random name out of the hat, the probability that I drew a female's name is 0.512. Okay, what's the probability of female given widowed? Now what am I doing? I'm restricting my search to here. What's that going to be? See, what is it? 11.9 divided by 15.2. What does that come out to be?
783. 3.78.
Y'all, are these two things equal?
No.
Then they are not independent. We just showed they're not. The fact that being widowed affects the probability of being a female and vice versa, they're not independent. Now, what if we'd picked the other way? What if we had said, okay, let's go with widowed first. What's the probability of widowed? And I'm going to pick 15.2 out of our 260.1. How much is it?
0.058.
Thank you. Okay, so now then, what's the probability of widowed given female? See, I've got to relate these somehow. So given female, now what's the probability of widowed given female?
0.8 or 0.089.
So 11.9, I'm just writing down the fraction first here. Don't want to do that. So 11.9, and then I'm getting to your good answer. 11.9 out of 133.2. And that's going to give me what now?
0.089. That's what that first leg, yeah.
0.89. Are those two things equal?
No.
No. So either way we go, it does not matter. It does not matter. Either way we go, we see that those probabilities are not equal. You have just shown that they're not independent. Look at one more. Different communication activities for folks. Random sample of teenagers. Are the events male and zero activities independent? Let's see. What's the probability of, you want to go with male or activities? Male. What's the probability of male here? 200 right here out of 400, right? So a half. What's the probability of male given zero activities? Okay, so now I'm restricting this to zero activities, which is going to be this. That's going to be 21 out of 42, guess what? Are those two things the same?
Yep.
Then we have just shown that being male is independent of how many, of 0 activities. In other words, male and female do the same amount of 0 activities. That's all that's saying. Gender does not affect 0 activities. How about female and 5 or more activities? Well, what's the probability of female? It is, just looking at the totals out there. What's the probability of female given 5 plus activities? So I'm going to take this thing. Maybe. Oh, come on. There it is. And move it over here. Now what have I got? 71 out of 109. What do I get there?
6.1.
Thank you. Notice, different. So if we're talking about folks that use 5 or more of these different communication things, a lot more likely to be female. So gender does influence that, whereas it didn't if there are no activities at all. So you can, this is how you show independence or not. It's that simple. And I could have turned that around. I could have said the probability of 5 or more given female, and I still would have gotten different answers. All right, y'all. That's conditional probability.